Hey guys, welcome back to another video. In this video, we're going to be talking about damping. Right, so what is damping? By definition, damping is the reduction in energy and amplitude of oscillation due to resistive forces on the oscillating system. What does this mean? So let's take an example of, again, the pendulum. So for this bob, if it oscillates, let's say from this position, which is over here, to let's say over here, right? So if the initial displacement or the maximum displacement is over here, and then it oscillates to this position and then oscillates to this position, if there is any sort of resistive force, let's say air resistance or resistance in this position, in this fixed point, or any sort of other external forces acting on the bob, there's going to be damping. What does that mean? That this object will start oscillating with decreasing displacement. So basically, if the initial maximum displacement was over here, after oscillating once, that initial displacement decreases and it goes up till here, and then goes up till here, then goes up till here, and eventually it will come back to equilibrium and will stop oscillating. If there were no resistive forces, in that case, it would keep oscillating on and on forever. But we live in a non-ideal world. So in that case, there is going to be some sort of resistive force, and it's going to cause damping, meaning it's going to decrease the oscillation, it's going to decrease its displacement, the amplitude, and the energy, since it starts moving with decreasing displacement. Right. So basically, we understand that as the object eventually faces resistive forces, it's going to decrease its displacement and its net energy starts decreasing because its velocity is also going to decrease. Its velocity is also going to decrease. Plus, its potential energy decreases as well, because initially, if the object's amplitude was over here, the height that it was displaced by was maximum h. Now, if the amplitude comes out to be over here after damping, now the z height, or the height displaced by for potential energy, decreases, is less than h. So basically, as damping happens, both amplitude and energy takes a hit. The energy decreases and the amplitude or the displacement starts decreasing as well. So basically, damping is in some cases useful. Let's say you have an earthquake and you don't want your building to fall off, because if you have a building, bad building, so if you have a building and it keeps oscillating, if it keeps oscillating back and forth, it's going to shatter and break off. So you need to introduce some sort of damping and some sort of mechanism to act like damping, so that you can reduce that oscillation, that heavy shaking, and make sure that the building is not affected. Similarly with flyovers, you want to make sure that the flyover does not oscillate in simple harmonic motion, and there is enough damping so that it does not break down, because with repeated back and forth movement, it's going to break down, right? So basically, damping is useful, and it's also a waste of energy if you don't want damping, and if you have any sort of mechanism where simple harmonic motion exists, due to resistive forces, your oscillation is going to take a hit. So now let's talk about a few types of damping. There are three main types of damping: light damping, heavy damping, and critical damping. What are those? Let's look into them one by one. Right, for light damping, what's happening over here is after you face those resistive forces, or the oscillating object, the oscillator, is going to face the resistive force, is going to continue the oscillation, but with decreasing amplitude every single time, right? So it's not going to instantly from maximum position go to the equilibrium and stop. Basically, if the bob was over here, for light damping, what's not going to happen is it's not going to go from the maximum position to the equilibrium position and stop. This is not going to happen. What happens is, for light damping, if you have a object oscillating, it's going to oscillate from maximum position then to a position with less displacement, and again to a position with even less displacement. But the oscillation is happening. The time period is not affected, but the displacement or the amplitude is affected, right? So it's still going to oscillate, have the same frequencies, have the same time period, but eventually, after a few oscillation, it's going to come to a stop. It's going to come to a stop. So it's basically going to take its time, continue its oscillation, and after a few oscillations, it's going to have reached equilibrium, right? So basically, the point of light damping is there is a decreasing amplitude, but the oscillation keeps happening, right? It still keeps going back and forth, but each and every time the amplitude or the displacement decreases. Great. So, by the way, if you notice the peak of the curves, it's going to look like y is equals to e to the power of x curve, basically the exponential curve. So, oh no, I mean, it's e to the power minus x. E to the power x is basically the pink curve that I've drawn, where this is 1, e to the power x, where if x is 0, y is 1. So this is your e to the power x, typical e to the power x curve. And your yellow curve, which is synonymous to the curve given by the peaks of your light damping, is actually y is equals to e to the power minus x, right? So this curve is actually e to the power of minus x. You don't need this, you don't need to know that, but if you're interested, if you want to know that how do I find out the amplitude of the oscillation at any given time, given there is damping. So in that case, what you do is, for a normal case where damping is not happening, the equation is given by, the displacement equation is given by x naught times sine omega t. Granted, you're plotting it against omega t and displacement. Your equation is going to be x naught amplitude times sine omega t. So let's say this is your normal simple harmonic motion curve. In this case, this is the amplitude and this is your omega t, right? So in this case, it's very simple. There is no damping. If you plug in the value of omega t, you're going to get the amplitude. But what if there is damping? You basically introduce e to the power of minus omega t over here, and you're going to have decreasing x value at every preceding instance. So basically, your displacement is going to decrease as you go forward in time. The more time you give it, your displacement is going to decrease and your amplitude is going to decrease. By how much? By e to the power minus omega t. So you introduce this variable and you're going to get the displacement at any given time, granted there is damping as well. So anyways, you don't need this. It's not in your syllabus. You don't need to calculate anything. You basically need to know and understand the theory behind damping, and that's enough for you. So one of the features of displacement by time graph for a lightly damped system is basically it's going to be a gradually decreasing amplitude exponentially, and it's, I guess, called an envelope shaped exponential decrease. Anyways, so first property is the amplitude decreases gradually and exponentially. The other thing to notice is the frequency remains the same, the exact same. And the other thing is time period remains the exact same since the frequency is same as well. So this is your light damping, where oscillation keeps happening. It does not come to a stop within the first oscillation. The oscillation keeps happening, but with decreasing amplitude every single time. That is your light damping. Next, let's look at critical damping. In critical damping, what's happening is within the first oscillation, let's say the object, this is equilibrium, and this is your maximum position. Within the first within the first oscillation, it's going to come back to equilibrium. It's not going to move down there. It's not going to move there. From this maximum displacement, it's directly going to come back to equilibrium. And the other feature of critical damping is it's going to do that in the shortest amount of time. In the shortest amount of time, which is why you're going to notice a steep decrease, a very steep decrease. So it returns to the equilibrium in the shortest possible time without oscillating. This is very important for critical and heavy damping. Even in heavy damping, you're not going to have any oscillation. So what was different with light damping though? The oscillation kept happening and it decreased gradually. In case of critical damping, and again heavy damping, we will go to that eventually. In case of both critical and heavy damping, it happens within the first oscillation and it decreases to 0 and stops. For critical damping, it happens in the shortest period of time. One example of critical damping is car suspension. You don't want your car to go bouncy. You want your car to take the hit and absorb the energy and move on. Right. So the features of displacement by time graph for a critically damped system is the oscillator does not oscillate. Its displacement directly falls to 0 in the shortest time. So for the graph, you're going to notice a fast decreasing gradient. And at x is equals to 0, which is over here, it's going to plateau and not increase or decrease, and it's going to stay horizontal. So basically, it has a steep decrease and reaches 0. X is equals to 0. Great. So that is your critical damping. If we move on to heavy damping, what's happening over here is, with heavy damping, a similar logic as critical damping, which is within the first oscillation, it is going to reach equilibrium. Within the first oscillation, it reaches equilibrium. It does not go over there. It stays over here. But with heavy damping, it's not going to take the shortest route. It's not going to take the shortest amount of time. It's going to take its time and slowly and gradually reach 0. A lot of cases for oscillating objects, you don't want the object to instantly reach 0. You don't want the object to instantly reach 0. You want it to take its time, take the hit, absorb the energy slowly. So the features of heavy damping is going to be no oscillation takes place. Again, the same as critical damping, but it has a slow decreasing gradient. And at x is equals to 0, the line remains horizontal over here. It does not increase or decrease. It plateaus down and it's going to be 0. Right, so that is your heavy damping, and these are the only 3 kinds of damping you need to know, and that there is. You don't need to know the formula, equation, you don't need to understand how the maths work. Right, you might be given graphs, you need to predict or apply which damping is appropriate and stuff like that. It's pretty simple and straightforward. So that is your damping.